Any problem with diffusion rates? Diffusion rates?
So that, like, you can't trust HP, they're cheap.
I love it.
How much does it cost you?
This was about like $650. I had $100 off, so that would make it $750, and then it was also tax free.
So this is tax free, $200 off of it in store, $650.
Wow.
Yeah, this thing is expensive.
I have questions.
What's your questions?
Everything on equivalent weights and all that stuff.
Okay, so that
Oh,
is
that's diffused.
the bottom part of the packet.
I got there, my phone, this one's black.
Oh, no.
Then why can't I because I'll grab my card from here, so we do.
But like, whenever he was doing it went completely over my head.
Okay.
Yeah.
See it?
I'm gonna go back to this page right here because it will really easily break it down. Well, I'm gonna do my best to try and explain it to you different ways so it seems a little better. So your molar mass is in units of grams per mole. Okay? And your charge is equivalents per mole. So if you want to know what an equivalence of an element is, it's just the charge. Not the charge per mole, but just the charge.
Just the charge in general?
Just the charge.
Okay.
So sodium is always a +1 because of its group.
Right.
Okay? But if we were doing the equivalence of, say, something like magnesium, its equivalence will always be 2 because its charge is always 2. So you always have to start with that part first. And both of these are things you should know. Now sometimes it'll be a problem that you're solving for. The part you'll be solving for will be the charge. Okay? That's the part you'll be solving for sometimes. The other part will be the molar mass if he says it's an unknown metal.
Yeah.
So you always want to set it up this way right here.
Okay.
You always want to set up in this way right here, where your equivalent weight, your total equivalence, is equal to your molar mass. Sometimes it'll be the molar mass of a compound. Sometimes it'll be a molar mass of just one element. So it's whatever its molar mass is off the periodic table. And then the bottom part, it's kind of hard to see on here, but it's the absolute value of the charge.
Okay.
So for your non-metals, you want that absolute value because we don't want a negative answer. We don't want all positive answers.
Does it have to be the absolute value every time?
Yes.
Okay.
Because in the case of something like oxygen, its charge or its preferred charge is what?
Isn't it 2?
Uh-huh.
Right.
It's -2 is what its preferred charge is. So we want the absolute value, so it's just 2. Because if you divide a positive number by a negative number, we're going to get a negative equivalent weight. And we want all positives.
Okay.
So that's as much math as you're going to have on the front end of setting up your equivalent weights.
Right.
Now where it kind of gets a little bit tricky is where we bring in some of the solving for charges, solving for equivalent weights, and solving for molar masses, and figuring out different elements and things like that. But equivalent weights are really awesome when you don't have the knowledge of what element it is, or you don't know what the balanced chemical equation is. Because normally we could run through something like this in a multimole conversion with a balanced chemical equation, but if you don't know it's titanium, or if you don't know it's lead, or if you don't know, or you're trying to find a new element and you don't know what it is, you can really easily solve out and eliminate things that it isn't, and it'll leave out things that it is. So the first problem he does, and I kind of pass by it and then come back to it, because this one's kind of a hard one, so we're going to come back to that.
Okay.
You need a little bit of practice before you do that one. So, starting off with these two, I scrolled up half of them, scroll back down. So we're just wanting to solve for equivalent weights and get you used to setting up the formula. So the equivalent weight of aluminum is, set up your formula, so your equivalent weight is equal to your molar mass over the absolute value of your charge. Okay. Always set that up first and then plug in the information you're solving for. So your equivalent weight is what we're solving for here. And it's going to be equal to the molar mass of aluminum, which is 26.98154. And the absolute value of your charge for aluminum, aluminum is one of the ones that you have to remember. It's one of your four you have to remember, is +3. So we want the absolute value of +3. Okay, this is a good review point for me to stop right here for the final. There is 4 transition elements that you will need to know the charge for on the finals. Okay, that's aluminum. Aluminum is always a +3 charge. Zinc is always a +2 charge. Silver is always a +1 charge, and cadmium is always a +1 charge. These are 4 that you can count on being on the final in either equivalent weight problem or some type of oxidation number calculation. Those are the only 4 that you will always know the charge of. Some people will throw dimercury in there, but dimercury can do some crazy things, so we stick to just those 4 there.
Are we going to get the review packet?
Yes and no. So you already have your review packet with the exception of test 5. Your review packet is your tests.
Oh.
Because it's not necessarily going to be the same questions, but it's going to be the same material. So it's a conglomeration of questions from the department and all the teachers that are teaching Chem 1. So the best way to study for it is to know the materials and know the material, and then you can understand different ways that it may be asked.
So like know it back and front, so you're not like, oh, I don't know how to do this one because it's asked me a different way.
Yeah, studying for the final, let me say this, studying for the final, don't go back and try and study everything.
Did you say study what you know?
Yes. Do not try and study everything. Study the things that you do well and do perfect on those.
How long is it?
It is an hour, let's see, it's 2 classes, so you have 2 55-minute blocks. So it should be right at an hour and a half, or really close to an hour and a half.
Is it like 200 questions?
I thought it was 2:30 to 4:20.
Yeah, that's an hour and,
Oh.
right? Yeah, hour 50. 2 55-minute blocks. What was that? I'm sorry, what was your question?
Is it like 200 questions?
It's 50 multiple choice questions.
50.
50. The only downside to your final is there is no partial credit. Multiple choice, the little bubble is either in the right spot or it's not. It's either colored in the right dot or not. So that's why we're saying do perfect on the things that you can and let that carry you.
Right before that, at 12:30.
We're gonna have some review over this weekend, and we're gonna have some more review coming up.
Okay.
So don't freak out. You're gonna have plenty of review. But yeah, that's why we say review the things, brush up on the things you're not okay with, and if you do have time, don't try and cram to learn them. But if you do have time, SI, me, Dr. Burns, Tutoring Center, get those things under your belt, especially if you're moving on to Chem 2. But last week of the semester is not a time to learn like 2 or 3 sections that you didn't do well on. Okay, so then this would be your setup for aluminum. Did he do all 4 of those?
I don't think so.
Okay, I'm going to do like 2 more. So for uranium, your setup is going to be the same, but then you're just going to plug in different numbers here. So the setup for it will be the molar mass, which will be 238.0289 over the absolute value of the charge. What is the absolute value of the charge for uranium? 5. He had to tell you 5. So you'll either have to tell you that because uranium actually has, if you remember back to our electron configuration, it has like 6 or 7 possible charges. So he'll either have to tell you what the charge is if he wants you to solve for one of the D transition group metals equivalent weight, or that may be what you're solving for. You may be solving for the charge, and you may have all the other information you need. So that would get you the equivalent weight for this one. Not 6, that should be a 5. And then let's do this polyatomic right here, because this normally trips people up.
Can you go over How you got those numbers?
Mm-hmm. So your 238.0289 is going to come off your periodic table.
That's just Formula
Mm-hmm. Yep, just molar mass. In this case, it's just the molar mass of the element. Here in a second, it's going to be the molar mass of that compound. But it's just your molar mass of your element here and here. And then your charge is the absolute value of whatever your charge is for that element in that particular case. So for aluminum,
Absolute value, I thought it was 1 plus 51 or something.
no, it's absolute value.
Okay.
Because for like all of your nonmetals are all going to be negative. So you got to do absolute value to get your non-negative answers. So for this titanium 4 sulfate, let me see this. This molar mass, unless someone else has done it.
I've done it. I think it's 240.0072.
I'm going to cheat with an app. I'm actually going to go a little bit further than you did. Not that your answer's wrong, I'm just going to go a little bit further out in decimal places. Mine is really close to yours. 239.992199. So yours would have been perfectly fine. It's just dependent upon, like, these periodic tables are older and a little bit more out of date than the AP ones we give you all. So what will be the absolute value of the charge for this one? You can use either one.
Titanium or whatever,
Mhm.
sulfate.
So you can use either one. Because they both have to be the same, right? There's no net charge here. So they both have to be the same. So what's the charge on sulfate?
2.
-2, but I have how many of them? 2. So you can either use the -4 part from the sulfate, or you know this titanium has to be a +4. You can use either one, the absolute value of either one's going to be exactly the same. So let's use the negative just to be different. We haven't used a negative yet. And then that's going to give you the equivalent weight of that compound. So these were individual metals, individual elements, and then that's the equivalent weight of a compound. Okay. So then we're given a couple of calculations here, and you're asked to go from grams to equivalents and some other units here to equivalents. So let's start off with the grams one and we'll work our way down here. So we're told we have 404.7 grams of strontium. So the first thing we want to do is start rearranging these conversion factors to put us in the units we need. So what's the only way we can get out of grams and into moles? It's the periodic table. The way we've done it the whole semester. Molar mass is the only way we can still get out of grams and into moles. So for strontium, we want to use 87.62 grams per mole. Okay? And that's going to get us out of that grams and into that moles. Now then, if you remember back, so you just use your molar mass. If you'll remember back to your setup for equivalent weight, we've utilized this conversion factor already, right? We want to utilize our charge now, which is in units of equivalents per mole. Well, that's great because we need to get out of mole and into equivalents. So what's the absolute value of the charge for strontium? 2. So for every 1 mole of strontium, it reacts in 2 equivalents. Exactly 2 equivalents. And then you calculate this out, and it's going to give you the equivalents for strontium.
How did we figure out the 2 equivalents just from the charge? Okay.
And the charge has units of equivalents per mole. And then you need to arrange them whatever way you need to in order to cancel moles, because we wanted equivalents here. If we'd wanted moles and we'd been given equivalents, then you'd flip the conversion factor to cancel equivalents and give you moles. So this is kind of taking what you know from the formula now and moving it into some stoichiometric conversions. Now we get into some more fun ones. So you can ask equivalents in some other units, so let's do it in molecules of fluorine gas going to equivalents. So we need to get out of molecules and into moles, because that's the only way we can get back into equivalents. What's our conversion factor to get out of molecules? So 6.022 times 10 to the 23rd molecules of fluorine is equal to 1 mole of fluorine. Now, what's the absolute value of the charge for fluorine? 1. So for every 1 mole of fluorine gas, it's going to react in 1 mole to 1 equivalent proportions. Which is going to let us cancel moles here and get into just equivalents again. Okay. Do like we just did in stoichiometric conversions. Follow your units for this. Okay. As long as you follow your units, as long as you're canceling along the way, you've got to get what you want, or you're going to see your mistake and you're going to be able to fix it. So this next one, we're given moles of sodium chloride, and we're wanting to get to equivalents. So it's actually already out of grams for us, and that helps. So this is not the case this time, but it doesn't hurt to draw out your formula and just kind of get an idea of what you're working with here. So you're working with 1 sodium, 1 chloride, a +1, and a -1. Okay, so our absolute value of our charge is going to be what?
What do you see?
1, right? You can use the positive portion or the negative portion. So for every 1 mole of sodium chloride, you're going to get 1 equivalence of sodium chloride. This one's kind of a fun one, this bottom one, especially after you all are just coming off of solutions. So you need to set this one up very carefully. So for 3.00 moles per liter of your phosphoric acid here, we immediately want to cancel our volume, right? Because we don't need units of volume for equivalence. So this would be 0.044 liters. Okay, and you want to multiply that by that first and get just this moles by itself. So you want to take this volume and you want to multiply that volume by your molarity. It's going to cancel that and give you just your moles. So then we can go straight from moles into equivalents. So the positive portion of this phosphoric acid is a +3, and the negative portion is a -3. So you can use either one. So for every 1 mole of your phosphoric acid, the contribution is 3 equivalents of phosphoric acid. So now you can do any calculation that we've done the whole semester now in equivalents. So before, when we told you at the beginning of the semester, you have to have a balanced chemical equation to do everything. Now you don't. We can give you any number and ask you to calculate any, really anything. Change in concentration, change in amount, change in molecules, change in mass, anything from that using equivalents. Okay, let's do this 21, and then we'll go back here. This eraser is awesome. Okay. Oh, he wants us to do it? Nah, I'm not gonna do that one. Unless somebody wants me to do that one, I'm not gonna do that one. I'd rather show you all the solving for the metal one. I'm gonna show you all that one. So this is pretty much a carbon copy of what kind of problem you're going to have on the test. Guarantee you're going to have one of these solving for what the metal is. Okay? Now, I would tell you to know it and know it quick. So first thing we're going to do is remember this equation, remember this setup here. Remember your units. So your molar mass is in units of grams per mole, your charge is in units of equivalents per mole, and your equivalence weight is just in units of equivalence. So we want to solve this problem. We're told it's an unknown metal. So before, when we had the benefit of knowing what the oxidation state of was the metal, we don't have that this time. But what we do have is the mass of the metal, an oxide that it forms, and then we're asked to do all the rest of the information. So we want to start off with this oxide. We know that it formed and reacted with this oxygen. So we're starting off here with 0.643 grams of oxygen. Be careful, oxygen's a diatomic gas. With equivalents, you can actually do this either way, but in all of your other problems, be careful using oxygen as a diatomic.
Is that the compound of the metal and oxygen?
Mm-hmm. Oh, I'm sorry. Yeah, subtract. Will somebody subtract that? So 0.544 minus the 0.643, and tell me just what the oxygen contribution is.
0.099 grams.
1099.
0.099 grams. Sorry, 0.0.
Like that.
99.
Is that right?
No, 0.099.
Like that.
Yes.
Mm-hmm. Okay. So then you want your molar mass for your diatomic oxygen. So 31.9988 grams per mole. Okay. The absolute value of your charge for your oxygen is what now? Because it's diatomic oxygen. You can do this either way, but really recommend you doing it this way. How many oxygens are there in diatomic oxygen? 2. What are each of them?
60. Wait, what are you talking about?
What are each of their charges?
Oh,
-2. So together they are -4. So it'd be the absolute value of -4 or just +4. So for every 1 mole of O2, you have 4 equivalents for diatomic oxygen. It will work out if you do it as just O, because you're going to have half the molar mass. You'd have 15.9994, and you'd have 2 equivalents here. So it'll work in the same proportions. But you need to get in the habit of remembering diatomic oxygen is one of your diatomics. So I recommend doing it this way. So that's going to give you the equivalents for oxygen. And we're stopping here because equivalents always react in 1-to-1 proportions. So whatever we get for the equivalents of oxygen, we had to have that many equivalents of our metal. So someone go ahead and do this calculation here.
So if you'd done 15.994 and then just done 2 equivalents,
2 equivalents.
it would have still worked out.
You'll get the same answer. What's somebody getting for that? And that'll be just units of equivalence. Because what we're interested in now is we can take that equivalence, and we know that equivalence of oxygen must be equal to the equivalence of metal. That's how equivalents react. They always react in 1-to-1 proportions. So now remembering back to your formula here, we want to start plugging in information we know.
Either 1, 2, 3, or 4.
What's that?
Equivalents. You gotta multiply it by 1, 2, 3, or 4.
Well, but we don't know the charge. But what can we look at? What do we have? What's the other piece of information we were given for the metal?
Metal.
It's a metal. We have what? How much of it?
It's with oxygen, so it's got to be either 2 or 4.
Well, it could be a bunch of different ones. It could be 6. But we do have the mass of the metal that was used, right? So we have that information. Where is it going to go? Hmm?
Oh, green.
The numerator. So you have the equivalent. You have the equivalents that reacted now. So equivalents of your metal. What we're solving for here. So what we're solving for here is the charge initially, right? And that's going to help us solve for our the metal and our charge for the metal. So let's see here. So we have our mass, and we know our equivalent weight now. So you have your equivalents, and we can get our metal here now. So 0.544 grams. We want to solve for the charge first. What are you getting for the charge?
33.891.
43?
Actually, I'm pretty sure it's 0.544 divided by 0.0124. And that equals 43.891.
Yeah, he does divide the 0.544 by.
Oh. It's not going to give you your charge, it's going to give you your molar mass. So molar mass is in units of grams per mole. So what you have here is you have a combination of the molar mass and you have a combination of the equivalents. Okay? So what units we're going to come out with is going to give us our molar mass here. So what was that? 43?
0.891.
Okay, so that's going to give you your molar mass of your metal. So what guy is that? Oh, Scandinavium. So Scandinavium. And Scandinavium can have a couple of different charges. What you'll actually do for this problem now at this point is this is when a little bit of Chem 1 review comes in. Remember when we did electron configuration in metals and broke them down by their charges?
No, that's not right.
That's not right?
Wait, there's another
Multiply
step
it.
though.
You have to multiply it by 2 in order to get closer to the atomic weight, or whatever.
Oh, that's right, because you have the 0.05 mole. Yep. So we need to do, now what is that? 86? What's it coming out to? 86, 87?
87.62. So then it,
Strontium.
yeah.
So we actually didn't get into that in empirical formula because we had to skip over it. You have to be close enough within 0.5 rounding of whatever element. So when we had Scandinavium, we were 43, we were a whole unit off. So you have to be close enough to really say that that's it. We weren't close enough. So you have to be within 0.05 of an accurate periodic table. So this would be strontium. Okay, strontium does only have one charge. What's the charge for strontium? +2. So if a strontium were to react with an oxygen, a strontium would react with O2. The charge on strontium is +2, charge on each oxygen is -2. So it would react to form strontium oxide. And I'm going to drop this charge here. So we need to balance it. We need a 2 here and a 2 here. Guarantee you're going to have one like that on the test. He probably will give you one, a charge of a metal you know. Because of the length of the problem, I would anticipate it being like a 15-pointer. With each step having its kind of own points. So if you can get to the point of getting the equivalence, that'll be so many points. If you can get to the point of figuring out the metal, that'd be so many more. And then getting the balanced chemical equation will be the last part. Another thing that you're just going to be able or be asked to do is just give reactions. So like these here. So we're told that zinc is reacting with lead-2 nitrate to produce solid lead. So let's just write out this reaction here. And this should hopefully really quick strike something that you know. What kind of reaction is that? One metal coming in, single displacement reaction. Yep. Okay. And we're told to find out how many grams of lead can be produced from 4.50 grams of zinc. So you start off with the zinc, and it's going to kick out the lead. How much lead is going to fall out? So we start with what we're given here. So 4.50 grams of your zinc. And all we can get out of mass and into moles is your molar mass. So your molar mass for your zinc is 65.39. So now we want to get out of moles and into equivalents. So zinc is one of the ones that you need to remember the charge for. So for every 1 mole of zinc, the absolute value of the charge for zinc is going to be 2 equivalents. Now what's actually cool with equivalents is you're using equivalents just like it's a balanced chemical equation. So if you didn't have this, if you didn't remember what type of reaction this is, you could cheat, right? Because you know when you're producing a solid lead coming out, you can do that and balance it, right? You can do that. Everyone can do that, right? You can do this reaction. If it tells you that you start with zinc and lead nitrate and you end up with just solid lead, everyone can do that reaction. So you can either now do it the molar mass way or you can do it the equivalence way, whichever one you're more comfortable with. You can do it both. But if we were to do it the equivalence way here, what is the charge on the lead there?